Which of the following is an incorrect representation of the shown diagram alongside? So if we start at north, do we go 40 degrees towards the west? No, we do not. We go 50 degrees towards the west, and therefore that is incorrect. Let's see what else we've got going over here. If I start on the west line, do I go 40 degrees towards the north? Yes, that is true. If I start 40 degrees north of west, so I'm going to start on the west line and go north of west, that is true. And then 320 means that I have to come all the way around. 270 plus 40 would be 310, not 320. So that one was also incorrect, which is a bit unfortunate, but both of them were marked as being options. Which of the following statements is true of a body that accelerates uniformly? Uniform acceleration is change in velocity over change in time, which means you have to have constant changes in velocity in constant periods of time. So it is the rate of change of velocity with time remains constant. Let's just look at the others. It's a rate of change of position. No, that would be velocity being constant. Its position changes by the same amount in equal time intervals. That is an equal change in position over time, which again is constant velocity. Its velocity increases by increasing amounts in equal time intervals. That's not constant changes in velocity in equal time periods. The graph gives a relationship between the velocity of a particle and time. Which one of the following graphs would best represent the relationship between the acceleration experienced by the body and time? So let's look at a graph. For a velocity time graph, acceleration is equal to change in velocity over change in time, which is equal to the gradient in this case. Now the gradient is constant. It is a straight line graph. So we are looking for a constant gradient throughout, and that is going to be option B. Two forces, 2 and 6 newtons, act at the same point. If the angle can be any value, which of the following cannot be a possible magnitude of the resultant force? Well, the maximum you can get from 6 and 2 is 8. The minimum you can get from 6 and 2 is 4 newtons. And any angle in between and any value in between is possible. So 5 is possible, 4 is possible, 8 is possible, 9 is not possible. The unit for electrical energy, any type of energy, will be measured in joules. It doesn't matter if it's electrical or otherwise. An electric toaster is connected to a 200 volt source for 1 minute. The current in the toaster is 2 amps. The work done by the toaster's element is. So we've got a whole lot of equations for work done, but what we want is we would like to use VIT because we've been given a V, we've been given an I, and the T is going to be equal to 60. So that lands up being 400 times 60, which is going to be 24,000 joules. A piece of rock with a mass of 10 kilograms is dropped from a rest on a planet called Lara. It attains a velocity of 4 meters per second in 2 seconds. What is the weight of the rock on Lara? The first thing that we need to do is establish the acceleration on Lara. So we are going to say V is equal to U plus AT. 4 is equal to, it starts at 0 plus I don't know A in 2 seconds. And therefore A turns out to be 2 meters per second squared. Now if I'm looking for weight, weight is Fg, which is equal to mass times gravitational acceleration. The mass is 10, the gravitational acceleration is 2, and therefore the correct answer over here is going to be equal to C, which is 20 newtons. Which of the following formulae for a stable compound must be incorrect? So let's take a look at all of the different options here. When I've got X2O3, I could easily have 2 X's and 3 O's. Remember that O has definitely got a valency of 2, So that means each of the x's would have a valency of 3. That looks possible enough. What about if I had PO4? PO4 has a valency of 3. It's PO4 3 minus. And then I've got a single x with a valency of 3. That seems reasonable enough. Then if we go SO4, it's going to look a lot like this one, SO4. The SO4s have all got a valency of 2, and therefore the X, there'd be 2 of them, and it would have a valency of 3. So that's all making sense so far. Let's try and draw out the next one. X, X, Cl, Cl, Cl. I know that each chloride has got a valency of 1. It is not possible to give these two X's the same valency. They are going to either, if they were both 2, it wouldn't match up. If they were both 1, it wouldn't match up. So that has to be a problem. The concentration of a solution containing 0,1 grams of calcium carbonate in 1,000 centimeters cubed of water is. First thing is we have to convert 1,000 centimeters cubed into 1 decimeter cubed. Then I need to say number of moles is equal to mass over molar mass. 0,1, it is in grams already, which is good news. The molar mass of calcium carbonate turns out to be equal to 40 plus 12 plus 48, and that is exactly 100, which is very convenient and cute. So that turns out to be 0,001. And then I say concentration is equal to number of moles divided by volume. 0,001 divided by a volume of 1 decimeter cubed, and therefore my concentration is going to be 0,001 moles per cubic decimeter. Finally, which of the following solutions will the sodium ions have the largest concentration? Well, here the sodium ions, there's 2 in each one, 2 in each one, 2 in each one, 1. So let's try. First I'm going to double that because the concentration of the solution, there's twice as many sodium ions. So if I just do that properly, it's going to be Na2CO3 is to the Na plus ion as 1 is to 2. So the concentration, because the volume isn't changing, is going to go 0,1 is to 0,2. So this one's got a 0,2 on the sodium ions. This is 0,3 on the sodium ions by the same logic. This is 0,36 on the sodium ions by the same logic. And finally, this one over here is a 1-to-1 ratio, so the sodium ions will have a 0,25 concentration. So the highest concentration is actually C. So you need to do a mole ratio there to make sense of it. A small aeroplane has taken off from Kimberley Airport and heads on a bearing of 310 degrees at 235 kilometers per hour. At the same time, there's a strong wind blowing on a bearing of 220 degrees at 45 kilometers per hour. Draw a neat labeled velocity vector diagram which can be used to find the resultant velocity. Now the important thing is that it does need to have a ruler. It doesn't need to be accurate in terms of measurement, but it must be neat and well labeled. So the first thing I'm going to do is I'm going to go to 220-ish. And I am going to draw myself a 45, and I need to label that 45 kilometers per hour. Then I say at the same time, we're going to go all the way around to 310. And I am going to draw a 235. So that's quite a lot longer. And I label it 235 kilometers per hour. That's done with a ruler. Now, how do I find the resultant? I complete the parallelogram of the two things that are happening at the same time, and I draw the diagonal of that parallelogram. I am then able to put in a little, I'm going to put a little alpha in over there. And then, so the first part was just to draw that diagram. Then calculate, not by scale diagram, you are obliged to calculate the resultant velocity. The good news is that there is a difference over here between 210 and 220 and 310 of 90 degrees, which means that I've actually got right-angled triangles all over the place here and can use sine, cos, and tan. So let's go ahead with that. First, I've got a right-angled triangle, so I can use Pythag. R squared is equal to 235 squared plus 45 squared, and I land up with R being, when I square root it, 239,27 kilometers per hour. In what direction? So I'm going to take that and I'm going to say, I know when I use this angle over here, this is my opposite, this is my adjacent, that's my hypotenuse. I know my opposite and my adjacent, so I'm going to go with tan. Tan of alpha is equal to the opposite side, which is 235, divided by the adjacent side, which is 45, and my alpha turns out to be 79,16 degrees. The thing is that that's not at anything, because it really is, if I'm going to go around, it starts at the bearing line and comes all the way around 220 plus those 79,16 degrees. So altogether, that's 299,16 degrees. So the resultant is equal to 239,27 kilometers per hour at 299,16 degrees. Now let's suppose that this pilot had initially headed on a bearing of 340 degrees. In other words, he had gone out in that direction. Let's try and look at what that would mean. Try another color. It would mean he came out like that, which means that my parallelogram would have landed up with a smaller resultant. So that resultant is not as long as the green resultant. So how do we express that? We are going to say the following. We can say, firstly, it asked me, will the resultant velocity increase, decrease, or remain the same, and explain. So I'm going to say it will decrease. There is a greater angle between the 235 kilometers per hour and the 45 kilometers per hour, and therefore a shorter diagonal. And what is the diagonal? It is the resultant.